So, welcome everyone to the fourth talk of the seminar series on design and programming cyber-physical systems and Internet of Things. We have the pleasure to have a talk by Professor Sanjoy Barwa, who is professor at the Washington University in St. Louis. Professor Barwa have been previously at the University of North Carolina, and the University of Vermont. His research interests, activities are in real-time systems, safety critical systems, scheduling theory, resource allocation in distributed computing. He's also a fellow of IEEE, and he received the 2014 Outstanding Technical Contributions and Leadership Award of the IEEE Technical Committee on Real-Time Systems. So thank you, Sanjoy, for accepting to be part of this seminar series. And please, we are looking forward to hearing from you. Please.
Thank you very much, Chadlia. Thank you. Can you all hear me well? Yes? Great. So I appreciate very much this opportunity to share some research ideas, what I consider to be some very exciting research directions with all of you. I am going to start sharing my screen now. And let's see if this works as advertised. Yeah, so let me just set things up a little bit so that there we go. So you can see me, yes? And you can see my shared screen. And I should let you know that I have my a chat box up open on the screen, so that if you have any questions that you would like me to respond to during the presentation, please type it into the chat box, or I guess you could enable your mic as well, but I will be monitoring the chat during the presentation. Okay, so let me start out by providing a high-level summary of the main message, the central thesis that I am going to try to communicate during this presentation. Oh, there you go. Yeah. So most safety critical systems are required to have their correctness validated, in some places formally verified before they are actually considered for deployment. In some application domains, such as civilian aviation, such pre-runtime verification is actually mandated by statutory certification requirements. Now, in order that you be able to verify runtime behavior beforehand, before it has actually happened, it is necessary, of course, that such runtime behavior be predictable beforehand. Indeed, this principle of predictability is one of the central cornerstones, one of the foundational principles of building safety-critical cyber-physical systems. So I will illustrate to you in a moment that there are at least two different kinds of predictability that are relevant to assuring safety: functional and timing predictability. Moez, I think your mic is on. You might want to mute it. Yeah, thank you. Functional and timing predictability. We should be able to predict what the system is going to do during runtime, and we should be able to predict when this is going to happen. Now, due to cost and related considerations, there has been an increasing tendency towards implementing cyber-physical systems, even highly safety-critical ones, upon general-purpose computing platforms rather than custom-built platforms. Now, these general-purpose platforms are characterized by the fact that they tend to exhibit significant variation and unpredictability with regards to their runtime timing behavior. The same piece of code, if you execute it again and again on the same platform, is likely to exhibit different timing behaviors on successive executions. As a consequence, it is very difficult to assure timing predictability for these systems. These are not time deterministic. So in response, the safety critical computing community has developed a series of design guidelines, design methodologies to follow in implementing safety critical systems upon such platforms. These design methodologies come accompanied with analysis techniques. If you implement a system following these guidelines, then these analysis techniques will allow you to predict to a high degree of accuracy timing properties of the system that are relevant to establishing safety. These design methodologies and the associated analysis techniques are often covered under the umbrella term of real-time scheduling theory, which is where I have my research interests and activities. Now, recently, over the past few years, there has been an increasing tendency towards incorporating learning-enabled components. Software components that are based upon deep learning and related AI technologies into cyber-physical systems, including safety-critical ones. And this throws up a challenge. Learning-enabled components, many of them, tend to exhibit significant variation and uncertainty with regards to their runtime functional behavior. So the question that I've been asking in my research in collaboration with a large number of other people is this: can the ideas and principles that underpin real-time scheduling theory that enabled us to achieve timing predictability of systems that are implemented upon platforms that do not exhibit timing determinism, can these same principles, these same ideas be repurposed, generalized, and reapplied to achieve functional predictability for systems that are safety critical and that use learning-enabled components? So this is the issue that we will be exploring during this presentation, okay? Let's dig right in. Let's start out taking a quick look at this principle of predictability and understand what it means for safety critical systems. For the purposes of illustration, here is a small part of the requirement specifications for airbags that are installed in cars. You can think of this as a canonical, if very simple, cyber-physical system. Now, to establish correctness, safety of such a cyber-physical system, you need multiple forms of predictability properties. There are functional predictability requirements. You must be able to predict the circumstances, the conditions, the events that will cause the airbag to inflate. There are also timing predictability requirements. You must be able to establish beforehand, rigorously, that the airbag will deploy within a specified duration of a triggering event. Now, both functional and timing predictability are equally important, equally central or critical to establishing the correctness of this particular cyber-physical system, to getting it verified, certified, if you will. But the fact of the matter is that the artifacts that we use in computing are explicitly designed to ensure functional correctness, not timing predictability. Think about it. Suppose you needed to write a function, to implement a function that would accept as input two floating point numbers x and y, and an interval duration t that is expected to be very small, and return the product of the two numbers within the specified duration. You would probably implement this to perform the multiplication operation as rapidly as possible and hope that the result is returned within the specified duration. If this appears unlikely, you would probably go out and buy yourself a faster processor. I'm not aware of any general purpose computing platform on which you can mandate, you can require that the result be returned within t time units. And the optimization criterion is that the returned value is as close to the product x times y as is possible. Stated differently, these traditional artifacts of computing look upon the process of computation as an optimization operation in which functional correctness is a constraint. You must return the right value, and timing behavior as an optimization objective. You want to minimize, maximize, in other words, in other ways, come close to a desired timing objective. Now, this is by design. This is not a mistake. This is what we wanted. These artifacts, these devices are implementing abstractions of computing, such as Turing machines, lambda calculus, etc., that start out seeking to strip away notions of time and other physical parameters in axiomatizing and thereby obtaining a formalization of the process of computation. This is what these devices are supposed to be doing. They are being successful in this. But this is something we need to keep in mind. We have kept in mind in building safety critical systems. So stepping back for a moment, what I've said is that since these devices assure functional determinism, we can achieve functional correctness, get functional predictability by appealing to the software engineering principle of correctness by construction. We synthesize our systems such that the synthesized system will possess the desired functional correctness properties. However, we can't synthesize our way to timing correctness. We must develop models of the runtime behavior of the system. Models are constructed before the runtime behavior actually happens. Develop techniques for analyzing these models such that on the basis of this analysis, we can come up with good predictions of what the runtime timing behavior is going to be. And as I'd stated, these analysis techniques and the models on which they're applied are what are collectively referred to as real-time scheduling theory. So this is the way things have traditionally been in the safety critical computing community. You construct a system to be functionally correct, you analyze the system using real-time scheduling theory to establish its timing correctness as well. Over the past few years, however, things have changed somewhat. We have seen an increasing use of learning-enabled components, these software components that are based upon deep learning and related AI technologies in our safety critical systems, including in the safety critical functionalities of these systems. Now, to understand why this should have been a game changer, why this should have made a significant difference to the way we build our systems, the way we understand them, it's necessary to understand a little bit of how these learning-enabled components work. And so I'm going to provide a brief, superficial, and not entirely accurate, but adequately so, discussion of a particularly commonly kind of learning-enabled component that you find in safety critical systems, deep neural networks. As I said, this is not going to be entirely correct. I'm going to simplify some details. I'm going to leave out some things, but it should be adequate for our purposes. A deep neural network is obtained by composing together software units known as neurons. You can think of a neuron as a function that accepts a number of real valued inputs and produces a real valued output. This output is generally obtained by taking the weighted sum of the inputs, offsetting this weighted sum by a parameter that is called the bias of the neuron, and then applying some nonlinear function to this weighted offset sum. The kind of nonlinear function we choose to apply here defines the kind of neuron we are using. We might, for example, have rectified linear units in which this nonlinear function is just taking the larger of 0 and this weighted offset sum. In other words, it always returns a non-negative value. Or you could have a sigmoid neuron in which this function is the sigmoid function you might remember from your high school calculus courses, or a few other choices as well. In any event, once you choose the form of the function, that is this function f, the precise function of its outputs that a neuron computes is determined entirely by the values you assign to the weight and the bias parameters of this neuron. So this is a single neuron. You build a neural network by composing together numbers of such neurons, generally in layered form as illustrated here. The number of layers will define the depth of the deep neural network. A deeper network will tend to have more layers than a shallower one. As you can see, the inputs to this neural network comprise the inputs to the neurons on the leftmost input layer. Therefore, each of these neurons is computing a different function of its inputs, this function being determined by the values you assign to the weight and bias parameters of each individual neuron, which will, of course, generally be different since they are trying to compute different functions. The outputs of the first layer will comprise the inputs to the next layer, and so on, until eventually the outputs of the rightmost layer comprise the outputs of the neural network. As is hopefully evident, The precise functions of the input that are computed by the entire neural network depend upon the values that you assigned to the weight and bias parameters of every neuron in every layer in this network. There will, in general, be tens, perhaps hundreds of thousands, even millions of such parameters in a single deep neural network. It is clearly not feasible for a human programmer to manually assign values to all these parameters. And this is where the learning aspect of a neural network comes in. Values are assigned to these parameters automatically by a process that is centered upon learning during a phase that is referred to as the training phase of the neural network that occurs prior to actually using the neural network. So you can think of the, I guess I should point out that this training phase requires the use of what is referred to as training data. This is inputs to the neural network for which you already know the desired output, the value that you want the neural network to compute, and you will use this training data to train the network to learn the weight and bias parameters of all the neurons in the network. You can think in a simplified form of the training process as proceeding in the following manner. You start out initializing the weight and bias parameters, let us assume arbitrarily. You execute the neural net on one set of training data. Observe the difference between the value that your neural network computes and the value that you wanted it to compute. In general, these will be different because you had initialized your parameters more or less arbitrarily. You then modify the weight and bias parameters of the neurons in order to drive down, minimize the difference between the computed and the desired outputs. This step again happens automatically according to rigorous mathematical principles that we won't go into over here, but you may be familiar with the notion of gradient descent for finding the minimal values of functions that you learned in multivariate calculus. Gradient descent techniques are used to modify the values of the parameters at a particular level. Once this has happened, the values that are modified get percolated through the network right to left via a process of backpropagation. So essentially, all the parameters in all the neurons are automatically updated so as to achieve a minimization of the difference between the computed and the desired output values. And once you've done all of this, you repeat the process on more training data and continue to do so until eventually you are satisfied that you have trained your network enough and it is ready for use in your actual cyber-physical system. Once that happens, what can you say about how good your neural network is? How effective is it in computing the function that you wanted it to compute? Now, the answer to this question depends upon a variety of factors, perhaps one of the most important of which is the quality of the training data that you had access to. How representative, in a very strict statistical sense, this training data is of the actual inputs that your neural network is going to encounter during actual executions during runtime. So there are some immediate consequences of this fact. First, unlike traditional computing components, which we had seen are able to deterministically guarantee functional correctness, functional correctness is not assured in a deterministic sense by deep neural networks for the most part. Any functional correctness guarantees that we are able to provide are necessarily probabilistic, not deterministic, not definite, not completely guaranteed to be true, except in a probabilistic or statistical sense. Furthermore, the viability, the validity, or the correctness of any such probabilistic functional correctness assurance is very much dependent upon how accurate our statistical models were of the inputs that we believe our neural network is likely to encounter during actual executions. And this has itself an important consequence. For events that are extremely unlikely to occur in actual execution, events that were basically unanticipated, the so-called black swan events, events that were not anticipated during system design time, but may end up having catastrophic consequences for the system. For such black swan events, the performance of a deep neural network is likely to be particularly poor. This is because the events were unanticipated, which means that they were not even attempted to be represented in the training data. These are very rare, so they were probably not encountered while profiling the system to achieve training data, and therefore they did not appear, and this is a completely unexpected scenario or situation that your neural network is having to face. So stepping back for a moment, what did we say? We said that in contrast to traditional computing components, which have a deterministic notion of assuring functional correctness, learning-enabled components tend to provide, at best, stochastic probabilistic guarantees. The validity of such guarantees depend upon the correctness of our probabilistic models for the inputs that the learning-enabled component will encounter during actual executions. As a consequence, the software engineering principle of correctness by construction, synthesizing a system to ensure that it has the correct functional, has the appropriate functional correctness properties, is not something we can depend upon if we desire deterministic functional safety, which we generally do. And additionally, and perhaps more important, if we are concerned about black swan events, as we generally are in safety critical systems, if we are concerned about these highly unanticipated events that can have catastrophic system consequences, if that be the case, then we should not depend entirely upon learning-enabled components to provide functional safety. We should have a backstop of traditional non-learning-enabled component backups that will assure safety in the event of such black swan events occurring. To understand this issue a little bit further, it helps to distinguish different aspects of the runtime behavior of safety critical systems. A safety critical system during runtime performs a variety of functions, some of which, hopefully a relatively small subset of these functions, are directly related to the safety of the entity of the device. The remaining functionalities seek to enhance the performance, optimize the mission of the safety critical system, but do not directly impact safety. You could think, for instance, about a car. The braking functions of the car are safety critical. The airbag functions of the car are safety critical. Perhaps functions concerned with active cruise control or ensuring you don't depart from your lane can be considered safety critical. But there are so many other functions happening on board your car. Fuel efficiency, ensuring that your ride is smooth, that it doesn't bump too much, that you meet pollution standards, that your car's infotainment system works flawlessly, that the climate control works well. These are all very important from a mission perspective. If your car performed poorly along these metrics, then they probably wouldn't sell too many units. However, they are not directly related to safety. We need to separate between the safety and the performance aspects of these of the runtime behavior in order to say that we want to assure safety to a very high level of assurance. Performance perhaps does not need to be assured to quite as high a level of assurance. With this notion, with this separation between safety and performance in mind, let's try to come up with a runtime architecture that incorporates the use of learning-enabled components in safety critical systems. During runtime, so this is showing a schematic of what happens during runtime, a learning-enabled component would do its thing, read in its input and compute an output. We would like this output to be evaluated by a monitor during runtime that will seek to determine the appropriateness of this output from the perspective of assuring safety. If the runtime monitor determines that this input is acceptable, this output is acceptable from the perspective of safety, and we will return in a moment and discuss the possible ways in which it could make this decision. If it decides it's acceptable from the perspective of safety, then this value actually gets used. If, however, the runtime monitor determines that it is unable to attest that the output of the learning-enabled component is adequate from a safety perspective, this triggers the execution of another software component based upon traditional, not learning-enabled technologies, which seeks to generate the output that is optimized from the perspective of assuring safety. So this is a runtime architecture. Actually, it's just a framework or a skeleton. Many pieces are unspecified that allow for the use of learning-enabled components in safety-critical systems. I want to emphasize that the learning-enabled component we have here is concerned with both safety and performance. It wants to ensure the system behaves safely and provides good performance. The runtime monitor is concerned with the acceptability of the output of the learning-enabled component for assuring safety. If this output fails to pass muster with the runtime monitor, then the traditional implementation, which is triggered, is concerned only with guaranteeing safety. Performance be damned. Hopefully, this will happen very rarely. I also want to emphasize that in this diagram, certain boxes are outlined in red and others, and another one in blue. I guess I should have thought of it earlier. If anyone is colorblind, the LEC box is blue, the runtime monitor and the traditional implementation are in red. My apologies about that. I just forgot about it till this moment. So the difference is that the runtime monitor and the traditional implementation should be developed using traditional techniques for developing safety critical code. These are using guidelines, using code development standards that are considered acceptable for safety critical system development, and in general are the kinds of techniques and the resulting systems are the kinds of systems that are able to pass statutory certification standards. Generally, learning-enabled components, at least today, do not pass certification standards at the highest criticality levels for highly safety critical systems. So here we have non-pedigreed, non-certifiable code generating an output, but it must be accepted by certifiable code or replaced by certifiable code from the perspective of safety before its output can be used for certifying safety properties. So this, as I said, is a general framework of an architecture for developing safety critical, for using learning enabled components in safety critical cyber physical systems. To continue or complete a discussion of what this framework would look like in any individual instance, we must instantiate this framework by explaining what runtime monitoring does and how it does it, what properties runtime monitoring should be required to satisfy, and based upon the kind of runtime monitoring we were able to do, how we would optimize system behavior, both during design of the system, in other words, putting together the components, choosing what learning-enabled component to use, etc., and during runtime, based upon the kind of information that the monitor gives us, what our future runtime decisions should be in order to optimize for performance, always without compromising safety. So for the remainder of this presentation, what I want to do is go through a few examples of instantiating this architectural framework by talking about different kinds of runtime monitoring and the associated performance optimization problems. What I will basically be doing here is showing you how, depending upon what the monitoring does, what optimization you can do by formulating optimization problems and maybe illustrating their solutions, but I will not actually be giving you algorithms for solving these optimization problems. I think coming up with the right problem is harder than actually solving the problem. For those of you who want to know how these optimization problems get solved, I'd be happy to provide follow-up references, okay? So let's instantiate this architecture in a couple of ways. First, let's suppose that our runtime monitoring is able to assign a numerical value to the quality of the output of the learning enabled component from the perspective of safety. So when is this possible? Let's take a simple example. Suppose our learning enabled component was trying to solve a computational problem that's very difficult, intractable to solve in general. For example, suppose it's trying to solve an NP-hard problem like a traveling salesman tour. You have a vehicle that needs to go certain places, and to do so optimally requires you to solve a traveling salesperson tour. That's an NP-hard problem. We don't know how to solve it efficiently. We can train a learning-enabled component to do this. The outcome of the learning-enabled component would be a tour, which a runtime monitor can very efficiently determine how much time this entire tour would take. If this leaves you with enough time from the safety perspective, then this output is acceptable. If it takes up too much time, it's unacceptable, and you must execute something else, some traditional implementation, which would probably be running a known approximation algorithm for traveling salesperson. There is an algorithm that guarantees to give you an answer that is within a factor 3/2 of the optimal tour. That's probably what your traditional implementation would do. It's a very fast algorithm. It just cannot give you the optimal answer, which is why you use the learning-enabled component. So we will look at problems where this is possible. You get a numerical value assigned to the result of a quality measure of the result of the learning-enabled component. So for this framework, when this is possible, let us consider as an example a multi-stage computation where we need to obtain a certain target value across all the stages. So I will illustrate this problem and its solution, though I won't tell you exactly how the solution is obtained, by considering a two-stage pipeline where you must obtain a target value of 10. We will in general assume that we have a choice of implementations for each stage. These would represent different algorithms for achieving the functionality of each stage. Some of these algorithms will be learning enabled, others will be traditional implementation. The model is more general. You could also think of the different implementations as representing the same algorithm implemented upon different platforms. For example, if it's a vision algorithm, you can implement it on a CPU versus a GPU. These will be different implementations of the same algorithm. But we will abstract out enough such that it doesn't matter what exactly these are. It's just that these are different ways of completing each stage of the pipeline. In my example, I will assume we have 3 implementations for each stage. Now, in general, as I had indicated earlier, we do not know before actually executing an implementation what its precise performance is going to be. And indeed, this performance may vary on different executions of the same implementation. It depends on many factors: the state of the system, the input, the actual input that is being provided, etc., etc. However, we need some form of characterization in order to be able to make any kind of performance guarantees. So in this example, we will assume that each implementation is characterized by an ordered pair of parameters. The first parameter represents a lower bound on the value that would be obtained by this implementation under very conservative assumptions about what's happening during runtime. So this lower bound is a value we can trust to a very high level of assurance, to a very great degree of confidence. So for the purposes of safety assurance, often safety certification, it is all right to claim that this particular implementation would actually achieve at least this value if it were to be executed. The second parameter simply represents an upper bound on the duration of time this implementation takes to execute. I will assume that each implementation of each stage is characterized by an ordered pair of parameters in this manner. Given such a system characterization, our objective is to come up with a plan for execution, and this plan should be obtained before we actually execute the system, to obtain a plan which guarantees to achieve the target value while seeking to minimize the execution duration that is taken in doing so. So in essence, we want to choose an implementation for each stage such that the cumulative value is guaranteed to be 10. And if there's a choice of many of them, we would like to choose the one that takes the least time to do so. In this scenario, we are looking upon the execution duration as a performance metric. We want to minimize the response time, while we are looking upon the target value as a safety constraint that must be guaranteed. So given such system specs, our solution approach is to synthesize a safe plan, a plan that guarantees to meet the target value under these very conservative assumptions of the lower bound. If we have multiple choices of safe plans, we would choose like the one that optimizes performance. In our example, minimizes the duration of the schedule. In this example, was there a, no, okay. Yes, Did someone? No? Okay. If you have a question or want to make a comment, could you perhaps type it into the chat box? That might be an easier way of interacting if you'd like to. Okay, I'll continue. So in this example, we had seen that there is a choice of we can see that there is a choice of several safe plans. We could execute each of the first implementations to get a total value of 6 plus 7, which at 13 is greater than 10. We could choose the first and second implementations of the 2 stages to get a total value of 6 plus 4, which is 10, or the second and first implementations to get a total value of 4 plus 7, which is 11, again, greater than 10. Amongst these 3 choices, it turns out that the one that minimizes the worst case execution duration is this one, since it takes 30 plus 20, 50 time units as opposed to 30 plus 50 or 50 plus 10. So this is the plan we synthesize prior to runtime. Now, during runtime, we will monitor the execution of the system. We would check to see how much value each implementation actually obtains. Recall that this plan is constructed under very conservative assumptions. 6 is a lower bound on the value that is obtained by the stage. During actual execution, it is likely that this very pessimistic assumption will not hold. We would actually receive greater value than implied by this worst case lower bound. Let us suppose that during some execution of our system, the value obtained by executing this first stage was actually 7 rather than the guaranteed minimum lower bound of 6. We can use the information that we have gleaned by such runtime monitoring to modify, optimize the remainder of the schedule, the parts that have not yet been executed, provided we are able to still guarantee safety. In this example, we see that the first stage gave us 7 units of value in the first execution, in this particular execution, which means to meet the target, we only need to achieve 3 additional units of value, which means it is safe for us to switch from the second to the third implementation of this final stage, thereby achieving further savings in the overall duration of the schedule. So the principle that is illustrated in this particular example can be summarized in this manner. We are designing the system beforehand to assure safety. And then during runtime, actually even beforehand, but primarily the significant part is that during runtime, we're optimizing this design in order to enhance further the performance. The building blocks of this method are as follows. Beforehand, we built a safe plan that guarantees correctness under these very conservative assumptions that are made regarding runtime behavior. This very conservative model is trusted to a very high level of assurance, and therefore we are assuring safety, just safety, at a very high level of assurance. We are guaranteeing the target value of 10. This plan incorporates within it considerable uncertainty, considerable variation, which is what the conservative model captures. We do runtime monitoring to resolve some of this inherent uncertainty. The pessimism disappears if actual behavior is not as pessimistic as predicted, and certain gains are achieved by this runtime monitoring. We thought we would achieve very little value, we achieved more value. This can only be detected during runtime by monitoring, and this detection will be different on different executions of the system. This additional knowledge obtained by runtime monitoring is used to enhance performance in the remainder of the schedule while continuing to assure safety. It is very important to recognize that safety continues to be guaranteed under the very conservative assumptions of the worst case models, the assumptions that are at a level of assurance to a degree of confidence adequate to guarantee, to pass the certification standards for safety. Nothing we have done, all the optimization we've performed, does not take away from the fact that safety is guaranteed under conservative assumptions. And in itself, this would be an adequate plan. This would be an adequate approach towards incorporating learning-enabled components into safety-critical systems. But we can often do better. We can do better if we have available to us additional information about the expected runtime behavior of the system. This additional information may not be as reliable For example, it may be highly probabilistic, may not be as reliable as the information, the deterministic lower bound information we used for safety assurance. But perhaps we could use such less reliable information to optimize further for performance. To illustrate this idea, I'm going to suppose we have a particularly simple kind of such less reliable information. In addition to these lower bounds that are guaranteed under all circumstances, we suppose we also have lower bound on the value that is obtained by each component, by each learning enabled component, under all circumstances except truly highly unlikely black swan kinds of events, truly pathological conditions. So you might be able to obtain such kinds of lower bounds by your process of profiling and training your deep neural net, or you might essentially be testing your deep neural net extensively after you've designed it to try and determine what kinds of performance range it would come up with on different inputs and take a very conservative lower bound on the observed values as opposed to on some statically analyzed values. If we had such values available to us, we would enrich, extend the characterization of our components. For our example, let us suppose that each component were characterized by an additional third parameter, which represents a lower bound on the value that would be obtained by this implementation under all non-pathological circumstances. Okay? So in this case, for instance, if you were to look at the second implementation of the first stage, we're asserting that under all circumstances that safety needs to be concerned with, we are guaranteed a value of at least 4. However, under most circumstances, under all non-pathological circumstances, under any circumstances that we could anticipate, or that our experiments covered or our observations covered, we actually get a far better value. We actually get a value of 6, which if you observe is 50% more. So it performs a lot better. We expect under all circumstances. However, we are only able to rigorously establish the bound of 4. If we have such characterizations of our learning-enabled components, we should change our optimization criterion. Right now, we say we want to optimize to enhance performance. Let's change this to say we want to optimize to enhance performance under the assumption that our typical conditions will hold. If typical conditions fail to hold, we are willing to live with suboptimal performance. However, we will not compromise on safety. Returning to our car example, for instance, an atypical circumstance, a pathological circumstance might include something you really did not expect your car to do. Maybe drive through a tornado or a Category 5 hurricane, especially in Tunisia. You don't have hurricanes and Category 5, tornadoes and Category 5 hurricanes in Tunisia. I don't think that we have them in America. So this is something you really don't expect to ever do. And so it's reasonable to seek to optimize the performance of your car, make sure that your fuel usage is efficient, to make sure that that your ride is smooth or that your entertainment system continues to work well under all circumstances except tornadoes and hurricanes. However, safety should be assured if, due to some strange condition in climate change, you end up with a hurricane or a tornado in Tunisia, or more likely, you decide to bring your car over to America, drive in Florida where they have Category 5 hurricanes, or drive in St. Louis where we do get the occasional tornado. So again, safety must be guaranteed under all circumstances, including the extremely unlikely one. It is all right to optimize performance for typical circumstances, provided typical circumstances cover the vast majority of circumstances or conditions. So let's revisit our example with this changed optimization criterion and this richer characterization of our implementations. Worst case behavior, typical case behavior, lower bounds, and this execution duration. Remember, we had identified several feasible schedules that are guaranteed to be safe. First implementation of each stage, first and second implementation, second and first implementation. And we had decided that the one that optimizes performance is this one. Now, when we have changed our optimization goals, we have said we only want to optimize under typical conditions, it turns out that we would actually synthesize a different plan, this one. How did this come about? I'm not going to tell you. I'll just show you what it does. As I said, for those who care, we can discuss an algorithm that does this. I can give you a reference to papers that discuss algorithms that synthesize this plan rather than the previous one. Now, this safe plan is different from the previous one, and under worst case circumstances, its execution duration at 10 plus 50 exceeds that of the previous one, which is 30 plus 20. However, this was constructed under very conservative assumptions. During runtime monitoring, we should, under typical circumstances, see that those worst case assumptions were unwarranted. In particular, it should be the case that in runtime monitoring, we would observe that the first stage, which was guaranteed to return only 4 units of value, is more likely to return a value closer to 6 or greater. Because, as I said, we're optimizing under typical circumstances. If this is violated, we're not optimizing. We're just trying to maintain safety. But when a value of 6 or greater is obtained, we are under typical circumstances. And now we can use this information to optimize the schedule further. In this particular case, we will see that we only need 4 additional units of value, which means it's safe for us to switch from the first implementation to the second implementation, thereby get a total response time of 10 plus 20, which is 30 under typical circumstances, rather than the value 50 we had obtained earlier under all circumstances. So let's step back for a moment and see what happened in this particular framework, in this particular scheme for incorporating learning-enabled components into safety critical systems. We required 2 characterizations of our components before they were actually executed. 2 characterizations of their runtime behavior. One was a very conservative worst case bound in behavior. The other was a characterization of its behavior under typical circumstances. Both of these are lower bounds. Only the worst case bounds are safe to be used for safety verification. This is mandated by statutory safety standards. Typical case characterization is perhaps what we should be using to optimize for performance for the mission of the cyber-physical system. The reason why it makes sense to incorporate learning-enabled components into safety-critical systems is because they have different characterizations with regards to worst case and typical case bounds. Learning-enabled components tend to exhibit very poor worst case bounds. This is because no one really understands how something like a deep neural network works. There are millions of parameters characterizing the execution of a deep neural network. To actually trace the behavior of this on a particular input is a hopeless task for human minds to comprehend. And so we make pessimistic assumptions at every stage and come up with very poor characterizations. However, they tend to work very well under typical circumstances, which is why we end up using them. Traditional components, in contrast, are developed according to software engineering disciplines that ensure that their worst case performance is not very bad. We do the best we can. It's usually not great, but nevertheless, it's not as bad as for learning-enabled components. However, even under typical characterizations, this performance is not as good as the performance of learning-enabled components tend to be. It is this dichotomy that gets teased out in implementations of safety-critical systems that incorporate learning-enabled components, but depend upon a safety backstop of traditional components. In the framework, we will build a safe plan prior to runtime that relies largely upon the traditional components. If during runtime, if in some way in this plan there is some flexibility, some slack, we don't have to use traditional components all throughout. The objective in the optimization, as formulated in the optimization problems, in the optimization algorithms that I haven't shared with you, the objective is to get the traditional components occur in the latter stages of the multi-stage pipeline. Then we use runtime monitoring to identify, to capture the pessimism that was built into the plans but didn't occur during actual executions. These runtime monitoring outcomes, the observations, should, under typical circumstances, show good performance. This savings over the pessimistic assumptions that we made can then be leveraged to optimize the remainder of the schedule, which typically turn out that what we are doing is replacing the traditional components that we built into the latter stages of the schedule in order to assure safety are now no longer needed to provide the worst case bounds, and therefore the poorer worst case bounds of learning enabled components will suffice, which means we can get the better performance of these learning enabled components in the latter stages under typical circumstances. So this was one kind of instantiation of this skeleton framework for real-time, for incorporating learning-enabled components into real-time, into safety-critical systems. This was applicable only when we could place some kind of quantitative metric value on the outcome of a learning-enabled component. And the example I showed, though that's not the only example, we assumed a multi-stage computation. It does not need to be so, but that was a good illustration of the use case where we can assign a numerical score to the outcome, to the value computed by a learning-enabled component. To look at another example, let's consider situations where runtime monitoring is not meaningful in the same sense. It can't really assign a numerical value to the output of the learning-enabled component. A classic use case of this in safety-critical systems is when learning-enabled components are used for perception, are used by the cyber-physical system to sense the environment within which it is operating, to understand the external world with which it is interacting. So one of the most common uses of learning-enabled components for the purposes of perception, and one that you may be very familiar with, is the use of binary classifiers for figuring out what the learning-enabled component, what the cyber-physical system may be encountering. So this is an example where you have, for example, a self-driving car. You have a camera on the car, which takes in images and seeks to determine whether this image contains a pedestrian or does not. Clearly, if there is a pedestrian in the field, then the car should be taking safety measures. If there is no pedestrian, it probably can try to speed up or whatever its associated performance metric is. This is a classic use of deep neural nets in cars for things like image recognition. The problem with subjecting this kind of classifier to runtime monitoring is that the classes to which the classifier is trying to categorize its inputs do not have precise, specific formal definitions. There is no formal definition in a mathematical sense of a pedestrian. You may be familiar with this very famous quote by the American mathematician Norbert Wiener, when he said that it's basically not very useful to model certain things. Models lose some fidelity, some detail. The best material model of a cat is another, or actually preferably the very same cat. Anything else is an approximation. So we don't really have mathematical models of a pedestrian. The best way of determining whether the classifier's output was accurate or not would be to have something that can identify a pedestrian. But if you could do that, you wouldn't be using this binary classifier, you'd be using that device directly. So that same framework doesn't quite work for perception specific learning enabled components. It is more useful to think about these entities as in the same way you think of conventional hardware sensors in traditional cyber-physical systems. Think of a thermometer or the device that measures the rotations per minute of the tires of your car, or something that measures wind speed. These are not formally proved as being correct. Instead, they are built, they're extensively tested, the test data is collected and shared with the relevant authorities, often certification authorities, who will agree or not that this device can be used in your cyber-physical system, in your safety-critical system. An important part of such a process of getting a conventional sensor accepted for use in safety-critical systems is that they should be characterized by quantitative metrics. For a thermometer that you want to use in a safety-critical system for a safety-critical functionality, this might include things like, this thermometer is guaranteed to be correct to a range of 0.05 degrees centigrade within -12 degrees and 85 degrees, 99.997% of the time. There will be some specific, precise numerical characterization, quantitative characterization of the quality of this device, and this characterization has to be accepted by your certification authorities by means of you making a persuasive argument as to why you believe in it. So we must come up with similar characterizations for our learning-enabled components to use them for perception. For a binary classifier, for example, the characterization might be something like this. We will have, by extensive testing, determined the duration it takes to execute and its false negative rate, the likelihood that it will fail to detect a pedestrian. And you do this by basically feeding it lots and lots of images during a testing phase. And some of the images will contain pedestrians, some will not, and you will determine the rate, the likelihood that it fails to detect a pedestrian. Hopefully this is very low, otherwise your classifier is not very useful. And you must convince your certification authority that your testing method was adequate. This is a social and cultural process as much as a technical one. This is something the safety critical community deals with. Unfortunately, current technology in learning enabled components is such that no individual classifier is likely to have a low enough false negative rate to be satisfactory for use in safety critical systems, which is why the solution that is actually used is to use several of them that all tend to be very different. You are aware probably that in cars, we have self-driving cars, for instance, you use cameras for visual part of the spectrum, you use radars, you might use LiDAR, and you would take the results from all of these and try to fuse them together in some sense. One particularly simple form of doing this is to assume that, from a safety perspective, if any of your classifiers flags a pedestrian, you assume a pedestrian is present. So the only circumstance under which you would get a false negative in the entire system is if all of them failed to flag a pedestrian. This would be very safe, but performance is likely to be compromised because you would flag pedestrians very often. If any of your classifiers gave the wrong answer, incorrectly said there was a pedestrian when there isn't one, your vehicle would, your overall unit would assume that there is a pedestrian and flag a false negative and take up and ignore performance to assure safety. So it's useful if you want to enhance performance as well, to additionally characterize your classifiers with this parameter, a false positive rate, which is the rate at which it incorrectly finds pedestrians when there aren't any. Again, this is obtained through extensive testing. With this complete characterization, you can create an optimization problem of determining what classifiers you should be executing in order to balance safety and performance. Here is a simple formulation of such an optimization problem. You are given n distinct classifiers. These are all different classifiers. They might be using different inputs, as I said, radar versus LiDAR. They might also be using the same input, but using different learning techniques. They may be different based upon different principles of deep neural nets, for example. From our purposes, all that matters is that each of these is characterized by an execution duration, a false negative rate, and a false positive rate. Your safety standards will tell you what the maximum acceptable error rate is. In other words, what is the acceptable thing that all of them will incorrectly say there is no pedestrian. You also will have some time constraint, a maximum duration during which you must decide whether there is or is not a pedestrian, because your control algorithm demands this. Given this, your problem is to determine which classifiers you should be executing. In order to meet the safety constraint, have your acceptable error rate not exceed P, and have your error rate not exceed P and the duration of execution not exceed D, and minimize the likelihood of a false positive. Minimize the likelihood that any of your classifiers will end up with the incorrect result, will incorrectly flag a pedestrian when there isn't one there. Once again, this is an optimization problem. It's not an easy optimization problem. It becomes a little bit easier if you assume the different classifiers are probably statistically independent. In other words, that their results don't depend upon each other, but that is generally not the case. There are correlations amongst the classifiers. Even assuming independence, this is a significant generalization of problems on maximum knapsacks, problems that you may have seen in in an algorithms course where you're trying to fill a bag to get maximum value, which are already known to be intractable, which are known to be NP hard. Nevertheless, these are optimization problems. Once you formulate the problem to represent the kinds of characteristics that you desire of your solution, it's up to the optimization research, those of us wearing optimization hats to figure out how to solve them. Formulating the problem is the challenge of the system architect who's trying to build the safety critical cyber-physical system. So I am running out of time, and that's all right because I'm at the point where I can conclude by highlighting the main points I've tried to make here today. I think it's inevitable that learning-enabled components will see increasingly more prominent roles in safety critical cyber-physical systems. The improvement in performance they offer is tremendous, and we as society are getting more and more ambitious about the functionalities we expect of our cyber-physical systems. This complexity can only be achieved by using learning-enabled components. As I have illustrated, unfortunately, learning-enabled components are functionally not deterministic in the way traditional computing components are. The safety critical computing community spent decades figuring out how to achieve timing predictability for systems that are not time deterministic. We are now needing to do the same thing of verifying functional correctness, achieving functional predictability for systems that lack functional determinism. The approach that seems particularly promising is to explicitly recognize the difference between safety critical functionalities and mission critical functionalities, which are not critical to safety, to depend upon runtime monitoring as an inherent part of system design. We will seek to optimize for performance while ensuring that there is always a path to safety from the current state of the system. This path to safety will typically depend upon traditional implementations, not including learning-enabled components, that provide some kind of backdoor to a safe solution, if not a particularly efficient from terms of performance one. Once you accept this general approach, agree that this framework is viable, the only challenge that remains is to construct optimization problems for the use of learning-enabled components, state this optimization problem by stating that safety is a constraint, performance, however quantified, an optimization objective, and then come up with algorithms for solving these optimization problems to maximize, minimize, whatever it might be, the optimization objective and thereby performance without compromising safety. I think that's pretty much all I had to say. Thank you very much for your attention. I'm of course happy to take any questions. Thank you.
Great. Yeah, thank you, Sanjoy, for a nice presentation.
Pleasure.
So are there any questions? So maybe I'll start with one. I don't know if I missed part of the presentation at the beginning, but so you mentioned at some point that these LECs, learning-enabled components, are, so the bounds, the worst case execution time bounds are very poor. But I kept thinking, why is this the case? So I guess if you're learning a decision tree, I can imagine that it's very difficult to predict time. But a deep neural network is a very regular structure. So is that what kind of algorithms are you?
I mean, an excellent observation, and apologies. I should have clarified. I was saying that the point I meant to communicate is that the functional behavior, the bounds we can provide on functional behavior tend to be very poor. Oh, okay. The bounds we provide on timing behavior for learning-enabled components, particularly deep neural nets, are fantastic. Right. Which is why in the characterizations I proposed here, I gave two estimates on the value of the functional behavior. I said a lower bound and a typical bound. But for execution time, I gave only one bound. You could, in principle, have two bounds, but they'll be very close to each other if you're using deep neural nets. So in a sense, it's ironic that we as a community spent decades figuring out how to deal with time variation with functional determinism guaranteed. If your learning-enabled components are primarily deep neural nets, time determinism is no longer such an issue because, as you observed, deep neural nets have a very regular structure, and nowadays they're all executed upon purpose-built hardware as well. Like there are special purpose chips optimized to execute them. So time determinism is suddenly available. Unfortunately, the other part of the pie, the functional determinism, went away. And so to some extent, you can think about this research, not what I talked about, but the general field as trying to see whether you can extend the lessons you had for time determinism, for time predictability to a different purpose, which is functional predictability. It's not quite obvious because time, has its own unique characteristics. You can't go back in time, you can't do many things, whereas, you can throw away functional values and so there are differences, but you got to the heart of the matter. Time is very deterministic in these systems.
Yeah.
Yes.
Okay, got it. Yeah, maybe I misunderstood, but yeah, excellent explanation. So also in that context where you have this graph, so when you presented the graph and saying if you manage to do better at the beginning, then you can relax towards the end. That sounds sounds very good. But it seems like it's very biased to saving things towards the end, or being able to use LECs towards the end of the chain. So that's why you proposed to do the traditional and then switch to LECs towards the end of the pipeline. But I was wondering if that is something that that really happens. So this bias about like becoming better towards the end of the chain. So maybe you have an application where there's a lot of things to save at the beginning of the chain, and I was wondering if that happens, or if that is just common that at the end of the chain you can save stuff. And if you have at the beginning of the chain, I can understand that this is challenging because you don't know what's coming afterwards, right? But you could maybe do this speculatively. I don't know.
So yes, that's. Again, what I was trying to do there was I was trying to provide intuition for something that the algorithms do. So as I said, I didn't discuss the optimization algorithm, but there is an algorithm which, given all these specs, will give you a schedule and will tell you how to switch back and forth during runtime based on what happens.
Right.
Now, these algorithms, if you run them on instances which are characterized by these pairs of parameters, by these 3 tuples of parameters, you just observe that greater use of the greater occurrence of deterministic components happens to occur near the end, and that's because the algorithm looks at the different options and figures out that these are the ones that are happening. If your implementation is such that all the deterministic components, the ones where deterministic components are a lot worse in the typical case than the LECs, if your application is such that those are only true in the earlier stages of the pipeline, then your optimization algorithm would not give you a good solution. So I was not proposing a heuristic. I was trying to provide an informal explanation for what the algorithm does, mainly because I didn't think it was worth describing the algorithm. That was not the purpose of this talk. But again, that's an excellent observation that what happens is an artifact of the algorithm's runtime, not of me guiding the algorithm to say at the beginning choose LECs, at the end choose deterministic. It's just what the algorithm ends up doing. I was trying to explain why.
Okay, got it.
Which is why I think, yeah. Okay.
Okay.
So I have a question. In order to formalize the optimization problem, do you take into account the switch time from one implementation to the other, or is it just something that will not influence the execution?
Yes, again, an excellent question. How does one actually formulate these optimization problems? My discussion here was abstract enough that you can do it as close to actual machine models or as much in the space of abstract design problems as you seek. The way I presented it here, I basically assumed that each stage is being done independently, and just before you start executing a stage, you have a choice of multiple implementations, and at runtime you will say, I will execute this function or this function or this function. So it's a runtime decision, and there is no significant state coming into that decision. And so there will not be a significant switch cost. There are circumstances, there are generalizations where each stage generates some state, and that state must be transmitted into the next stage, in which case there will be an additional cost associated with which stage you choose. If you chose a particular state in one state, implementation in one stage, then the execution time of, or the value obtained by the different states, by the different implementations of the next stage will be dependent upon the choice you made earlier. But I pretty much brushed those details under the carpet. I think those are worthwhile issues to explore as well. Yeah.
And at the very first stage, is the choice start from the beginning, and the other stages will derive what will be the most appropriate optimization, or is it speculative? I mean, at the first stage.
Yeah, again, that's an excellent concern. That's an excellent issue. So if everything was completely specified the way I have presented in this presentation for both the problems that I looked at, we have the parameters beforehand and we're trying to solve an optimization problem, then that solution would give you statically the first stage, right? Because there's nothing to monitor before executing the first stage. But in principle, in actual fact, what happens is that the problem formulation also generally happens during runtime. So for example, I talked about these classifiers, these binary classifiers with probabilities of false positive and false negative. The fact of the matter is that these probabilities actually depend upon ambient conditions. For example, suppose you're trying to determine if there's a pedestrian. Your radar will work better than your camera if it's very foggy, or pardon me, if it's dark and the lighting is poor. Whereas radar will not work very well if you're going into a tunnel or some such circumstances. So conditions will determine which specific what the parameters of these systems are as well. There are many different problems that get instantiated during runtime as opposed to beforehand. You still will have to make the entire scheduling decision before you start because you want to guarantee the safety of the entire pipeline, but it may not be something you do during compile time and just keep lying around. This will actually be a problem you're solving just before you actually begin your perception operation, for example. So, if everything was known beforehand, the first stage is static, just like you said, Shadlia. But if the problem formulation keeps on changing, then that's something you have to solve online. So one of the interesting issues from an algorithmist's perspective, which is what I am, I solve algorithms for a living, is that efficiency is very important in these problems because very often they are being solved online. If they were being solved offline, when you're building your car, you just put in the algorithms. You could just solve an NP-hard problem by using a lot of computation, but it's harder to solve these during runtime. Yeah?
Yeah, indeed. Yes. Thanks.
My pleasure. There is.
Okay, if there are no further questions.
I do have another question.
I have another question.
Of course, yeah.
About the runtime architecture, when you said that at some point you can move from LEC-enabled implementation to a safety-enabled implementation, and for the safety-enabled implementation, do you have such parameters like the worst case output, yes, the typical one, and the duration?
Indeed, again, a very good question. So generally, when you fall back, so this is the runtime architecture I proposed is a riff on something that's been around for a long time called the simplex architecture, SIMPLEX. This was proposed by Louis Shah in, I think, the early 2000s. And what you're basically doing is that all the time you're trying to optimize for performance by using, in our example, the LEC. Once you trigger the other thing, you're only concerned with safety at that moment. So in a sense, typical performance is not important. You are trying to optimize for safety. Having said that, in practice, it makes sense to have a safety, like within the constraints of optimizing for assuring safety. If you have multiple safe plans where one provides better performance than the other, it makes sense to choose the one with better performance, provided you are able to do it deterministically, provide the safety guarantee deterministically, because you do, like, once you go into an unsafe, once you go into the safety fallback, you would like to recover. You would like to again be able to provide good performance once the current threat to safety has passed. So you should optimize for it, but in the simplest forms of the problem that you see out there today, people tend to say that once you go into safety, we are only concerned with safety. But of course, in real life, to actually make this useful, you would need to not give up on safety, on performance entirely when you fall into the safety envelope, right? Very good observation, yeah.
And is it a kind of a knob-like adjustment specification so that you derive even the number of the implementation you are going to support?
I guess it could be done that way. Yeah, to my knowledge, right now it's just the algorithms that I've seen out there will just give you the specs for the LECs and the non-LECs, and the system will try to come up with an appropriate scheduling strategy. I've not actually seen this implemented in practice in actual systems, so I don't know how they would do it. Amongst other things, I mean, anyone who works with safety critical systems knows this. You have to come up with technical results, which is hard to do, but then you have to go through this social and cultural process of convincing industry, of convincing certification authorities that these are worth pursuing. You must remember that the safety critical systems industry is by nature conservative. The certification authorities, if something goes wrong, they get into trouble. If performance is improved, it's not like someone comes and gives them credit for it, right? So it's a conservative industry. You have to provide technical data to support a change in practice, which is what we're trying to do here. And then you have to go through a long, tedious process of changing the culture of an industry. And that is something I don't really get involved in. But so what's eventually going to happen, I don't know how they would do it. Right now, these are just algorithms, right? So a mapping to models, and then the models to algorithms. And then hopefully our industrial collaborators, the people who motivate these problems for us from industry, will find them worth implementing in their systems, and so then they would go off and take it into industry. That is the long-term hope, if you will.
Yeah.
Okay.
Thank you.
My pleasure. So I guess that's about it.